Hi everyone, welcome to my presentation. Today I'm going to present our paper, InaudibleKey, a generic inaudible acoustic signal-based key agreements protocol for mobile devices. So first, I would like to thank my collaborators for their contribution in this work. So this is the content for the presentation. So first I will talk about the background, and then I will talk about the system model, and then I will talk about the details of the system, and finally I will present the evaluation results. So we all know that IoT devices is becoming more and more popular in our everyday life. So we can see many IoT devices such as the smartphone, tablet, the smart speakers, and also smart home devices. So one fundamental problem is, as these IoT devices becoming more ubiquitous, so how we can pair different devices so we can secure their communications. So first, let's look at the current solutions. So the most common method is the preshared key, and this is an example of the preshared key. So this method has some limitations. First, it's vulnerable to the attackers, and secondly, it doesn't have any key revocation, and finally, it has low scalability. Another common method is manual pairing. So we need to select the device we want to pair, and then we need to enter the key and then click the confirm or the pair. So this method is labor intensive and also is not suitable for some devices that has small form factor, and also some IoT devices doesn't have any screens. And there is also another common method, which is the key exchange protocols, such as the DH protocol. And the traditional DH protocol is vulnerable to the man-in-the-middle attack, and the authenticated methods need the public key infrastructure. And also, there are some other methods, so like the NFC, scanning QR code. Unfortunately, this method can only work in very short distance. And so the question becomes how we can pair two devices safely in the pandemic, because we need to keep the social distance in the pandemic. So how we can pair two different devices that is far away from each other. So the NFC and the QR code doesn't work here. And also we need to look at what researchers do in the literature. So some solutions are based on the wearable sensors. For example, the walkie-talkie proposed in the IPSN 2016, so use the wearable sensors on the body to pair the devices on the same user. And also the Shake and Shock in Procom 2018 proposed to using the handshaking process to pair two wearable devices. And some other solutions are based on the radio signals. So some works are based on the channel reciprocity, and some other works are based on the physical proximity. So what is the research gap here? So since we already have so many solutions, what is the research gap here? So when we talk about a good key device pairing protocol or key generation protocol, we need to have three requirements. So first, it need to be fast. So we need to finish the device pairing very quickly. Second, it need to be practical. And thirdly, it need to be ubiquitous. So if we classify the existing methods based on these three requirements, and we can see that no solution can meet these three requirements at the same time. So either they are fast and ubiquitous, but it's not practical. And the ESBG and the CGC, they are fast and practical, but they are not ubiquitous. So our solution can meet these three requirements at the same time. So our solution can be fast, practical, and ubiquitous. So let's see the system model of our let's see the system model of our device pairing protocol. So our system is based on the channel reciprocity, so which means the acoustic signal between Alice and Bob are unique. Suppose we have two users, Alice and Bob. So Alice and Bob can exchange a number of packets using the inaudible acoustic signal. And based on the channel reciprocity, the acoustic signal, the acoustic channel between Alice and Bob is unique and is different from that of the if. For example, if we extract the channel features between Alice and Bob and also the Alice and if, we can see that the red curve and the blue curve are the channel features of Alice and Bob. They are very close, but the channel features between the Alice and if and also the if and Bob, so it's in black color, and we can see it's different from that of Alice and Bob. So based on the channel reciprocity, Alice and Bob can use their acoustic channel features to generate the same keys. So this is the basic idea of our system. And this is the flowchart of our system. So suppose we have two devices, Alice and Bob. They want to generate the same key. So first they will exchange a number of acoustic packets, and then they will follow these 4 steps here to generate the key, and finally they can use the key to secure their communications. So the key generation phase here includes 4 steps: the quantization, the anti-reverse engineering, the reconciliation, and the privacy amplification. So next I'm going to talk about these 4 steps. So how we design the transmitting signal. So we use the inaudible frequency range, which is between the 18 to 22 kilohertz. And we also use the OFDM modulation to modulate the OFDM symbols using the acoustic signal. And this method is proposed in the Finger I/O Kai 2016. So this is the diagram of how we transmit the signals. And Alice transmit a modulated signal to Bob, and then Bob transmits the signal back. And the transmitting interval between each packet is set to be 100 milliseconds. And after exchanging a number of acoustic packets, so we can extract the channel frequency response. So this graph shows the channel frequency response of Alice, Bob, and also the if. So the if is the attacker. And we can see the channel measurements of the Alice and Bob is very close, but the measurements of if is totally different. So Alice and Bob can use these channel measurements to generate the keys. So the first step is to use a multiple quantizer to quantize each sample into multiple bits. So this is the brief overview of how we can convert the signals into the bits. So we divide the signals from the maximum to the minimum into 4 areas, and the samples in this area will be converted to be 1, 1, and the samples in this area will be quantized to be 1, 0. And similarly, so we can get the bits for the samples in this area and also the bits in this area. And here we may notice that sometimes we may get duplicate bits here. So you can see we have a lot of 1s here. So later we will talk about how we can solve this problem. So after we get the binary bits, so we need to do one more step to until the reverse engineering. So the reason is some advanced attack methods can obtain the information from the binary sequence about the raw signal. So that means if the attacker gets these keys by using some more advanced attacking methods, they can get some information about the raw signal. So how we can solve this problem? So traditionally we can use the Bloom filter. However, the traditional Bloom filter does not reserve the order information. And in our paper, we use a special designed Bloom filter to reserve the order information. And here is the comparison of the traditional Bloom filter and our specially designed Bloom filter. So this is the Bloom filter, and suppose we have 2 inputs, the key 1 and key 2. So there is 1 bit mismatch between key 1 and key 2. So the mismatch is here. And for the traditional Bloom filter, if the output of the key 1 will become like this, and the output of key 2 may become like this, and we may find out that there are more mismatches. So the input, there is only 1 bit mismatch in the input, but there are more mismatches in the output. So this is the traditional Bloom filter. And so we use a specially designed Bloom filter. So the input is still like this, but the output can reserve the order information. So by reserving the order information, we means if there is 1 bit mismatch in the input, and there will also only 1 bit mismatch between the output. So similarly, if there are 2 bits mismatch in the output, so there will be 2 bits mismatch between the output. So this is the function of our specially designed Bloom filter. And this is an overview of our special Bloom filter. For the technical details, please refer to our paper. So first we will add some position bits for each bit. And then we will apply 2 hash functions to these 2 bits. And the output of these 2 hash functions will be projected to the Bloom filter, and it will form the output. And again, so this is just a very brief introduction. So for the more technical details, please find it in our paper. And so after the anti-reverse engineering, we need to do the reconciliation. The reconciliation is used to correct the mismatches between key Alice and key Bob, because usually we will get Alice and Bob approximately equal to each other. We cannot get a perfect matching. So in this paper, we optimize a recently proposed comprehensive sensing-based reconciliation method. So first, I will briefly introduce this method, and then I will present our optimization method. So the idea of this method is, suppose we have key Alice here, and we have key Bob here, and we suppose there are two mismatches here. And then the Alice will calculate Y Alice like this, and the Bob will calculate Y Bob like this. And then the Alice will send the Y Alice to Y Bob, and upon receiving the Y Alice, so Bob can calculate Y equals to Y Alice minus Y Bob, and it's equals to A times X. And because there are only two mismatches here, and actually the X is the sparse vector, and we can use the comprehensive sensing to reconstruct the key Alice, so we can make sure key Alice equals to key Bob. So this is the basic idea of the original method. And however, when we use this method, we find out that its performance is not stable. So this is because the matrix A here is either a random Gaussian matrix or a random Bernoulli matrix. So every time the A is generated randomly, so it cannot guarantee the performance. So we propose an optimization method. So our optimization method aims to minimize the MA. So the MA here means the mutual coherence of the A. So for the more details, please refer to our paper, because it's related to the sparse representation and also the comprehensive sensing. And also this is the how our optimization method works. So after we correcting the mismatches, we can get key Alice equals to key Bob. But we cannot use key Alice and key Bob directly. So there are two problems. First, so although the multiple level quantization can generate more bits, so it may sometimes generate some duplicate bits. So just like the examples here, sometimes in the bits we can have many ones or many zeros. So how we can solve this problem? So our solution is we use the KL transform to decorrelate the bit sequence of the reconciliation. And there is another problem. So although the reconciliation method can improve the reliability, so it reveals some partial information to the if. So that's because, remember, in this reconciliation process, Alice need to transmit the Y Alice to Y Bob. So the attacker can get the Y Alice, and it can use some attacking methods to get some information about the original key. So this will weaken the security of our system. So we use the dual hash function to remove the revealed information from the generated keys. And finally, we generate the two keys for Alice and Bob, and they can use these two keys to secure their communications. So here is the evaluation setup. So we evaluate different devices in different environments and at different distance and also different SNRs. And we use three metrics: the key matching rate, the key generation rate, and also the success rate. So first, let's see the system performance and the different environments. So this graph shows the key matching rate of different distance, and we can see when we increase the distance, actually the key matching rate drops slowly. So this is because the signal becomes much weaker, and there will be also much more noise in the signal, so the key matching rate will decrease slightly. But still, our system can achieve very high key matching rate within 200 meters, 2 meters distance. And this graph shows the success rate of different environments: the coffee shop, shopping center, bus station, and the metro station. And we can see for the coffee shop and the shopping center, we can achieve very high success rate. But for the bus station and the metro station, though, the success rate drops. So this is because there are more noise in the bus station and the metro station. And this table shows the success rate of different devices. So we can see for the smart devices, Samsung, HTC, and Huawei device, we can achieve very high success rate. But for the low price IoT device, for the Arduino, so the success rate drops, but still we can get more than 80% success rate. And also this is where we can improve. So based on the results here, we can draw the conclusion that the key generation rate of our system is between 700 to 800 bits per second. So which means our system is fast, and our system can work in the range of 20 centimeters to the 2 meters. So our system is very practical, and also our system can work in different environments, which means our system is ubiquitous. So we can say our system meet the requirements of a good key device, key generation protocol. And also we measure the energy consumption of our system for different devices. We measure the energy consumption on the Samsung and also on the Arduino, and we can see our system require less energy consumption than some competitors. And if we consider about the battery budget, so with only 1% of the battery budget, so our system can run about 175 times per hour on the Samsung smartphone, and also it can run 3 times per hour on the Arduino board. And we also analyze the security of our system. We consider 3 attackers: eavesdropping attack, imitating attack, and also the predictable channel attack. And here is the result, and we can see the key agreement rate for the attackers is much lower than the real users, and so it can at most get about 42% of the matching rate. And more importantly, although they can get about 40% matching rate, they have no idea which bits are correct and which bits are wrong, so that will still make our system secure. And we also compare our system with some of the state-of-the-art. And here is the benchmark we used in our paper, and here is the results. So we compare the key agreement rate, the key generation rate, the entropy, and also the reconciliation counts. So you can see our system is outperforms the other method in these 4 metrics. And for the key agreement rate, so our system ranks the second. So the first method is called the TDS. It can achieve very high key agreement rate because its working distance is very short. It's only less than 5 centimeters, which makes this system less practical. So we can see that our system can generate more keys and achieve higher key matching rate, and also achieve higher entropy, and only require less reconciliation counts compared to other methods. And so now let's look at a short demo of our system. Okay, so now let me conclude our paper. So in this paper, we designed an inaudible acoustic signal-based device pairing system, which is called the InaudibleKey. So our system can be used to pair personal wearable devices as long as they have a pair of microphone and speaker. Our system can also be used to pair smart home devices and to pair 2 devices without breaking the social distance. So that's all. Thank you.